a love story at the edge of our solar system, and studying centaurs. You're listening to Are We There Yet?, the radio show exploring space exploration. Hi, I'm Brendan Byrne. With Valentine's Day quickly approaching, love is in the air on Earth and in space. Researchers have uncovered evidence that Pluto may have found one of its mates, a moon that is, through what they call the kiss and capture method. We'll speak with NASA's Adine Denton about her research on the small dwarf planet and its largest moon. Then, one centaur, the space variety, has sparked attention amongst researchers. Chiron has characteristics of both a comet and an asteroid. We'll speak with researchers Noemi Palanilla Alonso and Charles Shambao about their recent findings. That's ahead on Are We There Yet? Earth's moon formed after a huge object crashed into our planet, sending debris out into space that got caught in our orbit and eventually became the moon we know today. Astronomers once thought that this is how Pluto managed to collect its large moon Chiron, but now new research says the moon's story may have been much calmer. That calmer method is known as the kiss and capture, where Pluto and its large moon gently collided, resulting in Chiron staying in the small dwarf planet's orbit. Here to talk more about this new hypothesis and her research is Adine Denton, a NASA postdoctoral program fellow. She spoke with Are We There Yet's producer Marianne Summerall about Pluto and Chiron's backgrounds and characteristics.
Adine, welcome to the show.
Thanks for having me.
So before we kind of jump into this unique moon and what you found with your research, astronomers have tried to understand how Pluto has a large moon like Chiron. Chiron is a pretty big moon in comparison to Pluto. Just to paint a picture, how big is Chiron in comparison to this dwarf planet?
Chiron is weirdly large compared to Pluto. It's about half its size and 12% of its mass. And that's pretty unusual because if we look at other solar system moons, like, say, Phobos and Deimos are the two moons of Mars, they're a small fraction of a percent the mass of Mars. Similar are the moons of the giant planets. So the only other comparison point we really have is our moon, which is also weirdly large in comparison to the Earth.
So originally it was theorized Chiron was created similarly to how Earth's moon was created, right? But this new research you've collected has a new theory, right? But why was that old theory so widely accepted? Why did scientists think Chiron developed just like our moon?
Well, the thing is that it's pretty hard to get a really big moon around a planet. Like, it's just a difficult thing to do. The reason why we think the Earth's moon forms from a giant impact is partially because it's really big relative to the Earth, but also because the Earth-moon system has a lot of angular momentum. So the amount of energy that's contained in the spin of the Earth, the spin of the moon, and how the moon revolves around the Earth, all of that combined is a lot of energy relative to the size of the bodies. So something had to have happened to give us a moon that is unusually large and that also imparted a lot of energy to the system. So those two things combined, plus the knowledge from Apollo samples that the Earth and the moon are very chemically similar in a lot of ways, led people to suggest that, the easiest way to impart a bunch of energy to the system and get a big moon kind of locked around the Earth would be if a Mars-sized object hit the Earth early on its history, and then you capture a moon out of that process.
Right. And so then with Chiron, that was kind of assumed that a similar process happened, but it didn't explain some key characteristics that you kind of pointed out in your research, right? What were some of those key characteristics?
The problem with the Pluto-Chiron impact is that we do think, and my work still shows that it probably was a giant impact of some kind that allowed Pluto to capture Chiron, but it was the actual materials involved that make things a little bit different. So when Pluto and Chiron collide, it's still a giant impact, right? Two planetary-sized bodies are still hitting each other. But there's a massive difference because Pluto and Chiron are a lot smaller than even the Earth's moon. And they're also made of rock and ice instead of rock and metal, which is what the moon and the Earth are made out of. And what that means is that the impact, it turns out, is a lot less intense. So the Earth and the moon collide at tens of kilometers per second. It's really fast. Stuff's vaporizing, stuff's melting. It's not a good time. When Pluto and Chiron collide, it's a relatively gentle collision at around 1 kilometer per second. And that sounds really fast, right? Fighter jets travel faster than that. It's not very fast. It's actually on a planetary scale quite gentle. When we actually look at how that plays out, what we find is that Pluto and Charon collide and they kind of briefly merge with each other and then slowly separate to form the system that we see today. So even though a giant impact is the source, the actual process by which Charon gets captured as a moon is very different from how the Earth captures its moon.
I saw it's being called the kiss and capture method, right? It's kind of like what you said, it's a little bit slower and then it collides. But why is it called kiss and capture? I'm just curious of this name. Why is it called kiss and capture?
Yeah, we call it a kiss and capture to delineate the fact that it's a form of satellite capture. That's where the capture comes from. That's a little bit unusual. Previous simulations, and these are all computer simulations that we're doing to look at planet-on-planet collisions, because fortunately we have not had the privilege of seeing what happens when two planets collide in real life. So previous examples of this have been mostly studying the Earth and the Moon's formation. And that process is, like I said, very violent, very dramatic, and also very destructive for both bodies. The description of kiss and capture reflects the fact that this new mechanism causes Pluto and Charon to briefly merge together with each other. That's the kiss. And then they slowly separate, and that's the capture. And previously what would happen is a large object would come in and potentially hit Pluto and keep going and then get caught in its gravity field and then be captured as a satellite. But now that we've updated our codes, that's not what happens. Instead, Charon comes in, hits Pluto, penetrates a little bit of the way into Pluto so that the two bodies get stuck together. But Pluto is eventually able to push Charon back off, and Charon says, okay, that was nice. I will be over here now, and establishes itself as a satellite.
That is fascinating. And going back to your point, I don't know if I want to see two planets in our solar system collide in my lifetime. So I'm glad that we just have data and models for that. And I want to go in a little bit of a new direction. For being a dwarf planet and having this giant moon and also several other moons, is that normal for something the size of Pluto?
Well, it sure depends on where you are. So yes, Pluto does have not just Charon, but 4 other little moons. They all look like potatoes. They're Nix, Styx, Kerberos, and Hydra. And they're orders of magnitude smaller in mass than Charon. So like think 1% the size, these little guys. They really are just little guys. So Pluto does really have this whole system where it has one big moon and then a bunch of little guys. And we're not really sure how Pluto got the little guys. They could have been debris that was kicked off from this initial collision. So Charon hits Pluto and then they both lose some of their ice and it forms this outer debris disk at the edge of the system that could then coalesce into these other moons. We're not quite sure. If that's the case, then this is all pretty self-consistent. You just hit Pluto one time and you get 4 moons for the price of 1 impact. But when it comes to thinking about, is that normal? In the Kuiper Belt, it actually might be. So Pluto and Charon are, of course, not alone in the Kuiper Belt. That's why Pluto is no longer a planet. And the interesting thing about the Kuiper Belt is that 8 out of 10 of the largest Kuiper Belt objects also have a relatively large moon. That includes Eris, the object that was discovered back in 2003 that was found to be the same size and like slightly more massive than Pluto, which is why Pluto is no longer a planet. Very sad. It has its own little moon called Dysnomia that's relatively big. And as we go down the list, Haumea has 2 moons that are pretty big, Orcus has Vanth, etc. These bodies all seem to have at least one relatively large moon, which suggests that yeah, maybe this did happen all across the Kuiper Belt.
So this research, there's this new way that Pluto could have captured Charon. Could this also lead to maybe some other theories that this method could have been used on some of the other planets that are in our solar system, or maybe even exoplanets outside of our solar system?
It depends, right? Because what we found is we tested this mechanism for some of the other Kuiper Belt objects, and it works for a lot of those. So for this kind of size range of object, for stuff that's made out of ice and rock, that's around the size of Pluto or smaller, this definitely works. But at some point, it depends on the planet, what it's made out of, and also how big it is. As planets get bigger, the collisions between them are naturally more intense. And the reason for that is when two planets collide, it's very different than when, say, an asteroid hits the Earth, right? An asteroid that hits the Earth is effectively accelerated by the Earth's gravity, and the speed at which it hits the Earth depends on it getting pulled towards the Earth. When two planets collide and they're similar in mass, it's not the same kind of basic physics problem. They're being pulled toward each other. It's kind of a mutual gravitational attraction. And the bigger you get, the stronger that gravitational attraction, right? So when two bodies that are the size of the Earth collide, they're colliding much faster because there's a lot more gravitational attraction between them than, say, Pluto and Chiron. So at some point, kiss and capture isn't going to work because they're going to be hitting each other so much faster that stuff's going to start flying off and stuff's going to start getting vaporized and melted, and you're looking at something else entirely. But yes, I would say this probably could scale up from Kuiper Belt objects to smaller, icy exoplanets.
Could this explain some of the earlier things in our solar system that were created? I was reading some of your research. Could this potentially have occurred in the early development of our solar system?
When we think most of these large collisions would have happened, which is cool for us because they're not happening now, the solar system we generally think is formed from, you have this disk of gas and dust that's around the young sun, and that dust starts to condense into pebbles that form planetesimals, and then eventually somehow you get to the modern solar system, which means there's a period in which you have these little baby planets that we call planetesimals that are flying around, and there's a lot more stuff. And that stuff is the stuff that forms planets by having two things collide to make a bigger thing. So this would have been the first tens of millions of years after the solar system formed. So again, like 4 billion years ago, et cetera. And during that process, you start forming stuff like the giant planets, but you also start forming stuff like the Kuiper Belt gets put into its current position because Jupiter moves around and tosses a bunch of stuff out into the Kuiper Belt. And at some point there's probably when Pluto and Chiron collided and became the modern system that we now see. So this was probably more than 3 billion years ago.
And Adine, I want to end this fascinating conversation on another note, which is for a lot of people, Pluto has a very special place in our hearts. I already heard you say, obviously, it was sad when we saw it not classified as a planet anymore. I was also pretty sad myself. But what got you into studying Chiron? Have you always had this love for Pluto? When did this research kind of start, and how did you get here today?
In one sense, I've always thought Pluto was really neat because I think the outer solar system is really cool, always have. But I was an intern at the Lunar and Planetary Institute, which is just outside of Johnson Space Center in Houston, the summer that New Horizons flew by Pluto. So that was in 2015. And I was a college student, and a lot of the people that worked on that mission worked there, and I got to see some of the data coming back. And I was just so taken by Pluto because the pictures we have are incredible, right? Pluto is incredibly geologically active. Everybody was worried that we were going to fly by Pluto and it was going to be kind of this dead world. Not much was going to be going on, but instead it had so many things going on. And I was just absolutely captivated by everything that I saw there. Pluto's heart, its mountains, its glaciers. And I wanted to know how it all works. So eventually I did end up getting a PhD studying Pluto because I just think it's so neat. So I got my PhD studying Pluto's heart, how the heart forms. And then after that kind of expanded my scope to, well, how did Pluto and Chiron get there in the first place? And that's what led me to the research that we're talking about today.
And I'm looking forward to hearing more about Pluto news. Thank you so much, Adine, for joining us today.
Thank you for having me.
That was Adine Denton, a NASA postdoctoral program fellow, speaking with Are We There Yet's Marion Summerall. Still to come, a comet asteroid hybrid. That's ahead on Are We There Yet? You're listening to Are We There Yet? I'm Brendan Byrne. Right now, we're talking about centaurs. These are small bodies in the solar system that formed from the same disk of gas and dust that the planets formed from, but they're too tiny to be a planet. And thanks to findings from the James Webb Space Telescope, one centaur may be more unique than previously thought. Chiron has characteristics of being a comet and an asteroid, and it has some of the key building blocks of life as we know it here on Earth, like carbon dioxide and methane. So could Chiron lead us to answers about how our solar system was created, or where we came from? Well, here to answer those questions and talk about their research on the composition of Chiron is the research team leader, Noemi Peanila Alonso, a distinguished professor at the Institute for Space Science and Technologies in Asturias, Spain, and Charles Chambeau, a research assistant professor at the University of Central Florida. Noemi, Charles, thank you so much for joining us.
Thank you.
What is a centaur? It's got a cool name, I know that, but I know nothing outside of that. What is a centaur?
A small body in the solar system, and it means that it formed from the same disk of gas and dust than the planets formed, but it did not accrete enough mass, so it has been, since formation, smaller than the planets. And this particular class of small bodies, because we know the asteroids, we know the comets, we know Pluto, that the trans-Neptunian objects, but the centaurs are like transitional objects that were born very far from the sun, so they are covered by ice and they have a lot of ice in the inner layers. But they move closer to the planets and sometimes they behave like comets. So it's like an object in transition from the icy bare bodies, the comets with comas and tails and all the fascinating dressing up that the comets have.
Charles, how do you actually locate centaurs using something like JWST?
So with JWST, the discovery and location is done with more ground-based telescope facilities, where they're far away, but they're actually relatively bright, some of them, due to their larger sizes. So we can detect and find them. It's the characterization that's really difficult. And so that's where Webb really was this new kind of tool that we could use where we could really characterize them well. And so that's really where Webb's kind of strength came from. Where before Webb, we could find them, but we couldn't really say much about them. With Webb, now we're actually really kind of digging deep into what are they composed of, what are the gases that are surrounding them, that then explain more about their bigger questions of like their interior structures, how do they form, that then get linked to the early solar system formation models.
Noemi, what did you discover about this particular centaur?
First, let me tell you that what we do to characterize these objects, what I do with the program that we run, is to study the surface composition. So we do spectroscopy. We don't do cool images like when you see the images from galaxies or clusters of stars, of these kind of things. And with the spectroscopy, what we get is the reflectance of the surface at different colors that, depending on the color that is present or is absent on the reflectance, we know which material is on the surface absorbing that light. So in particular for Chiron, what we observed was so different from what we were expecting. We found absorption bands that indicate ice is on the surface, but we also found emission bands that indicate that it is active and it has a very cool coma around. So for example, we know that this object has a coma with carbon dioxide and with methane that are kind of volatile species, but not the most volatile, not the ones that switch from ice form to gas form easily. And it has also an ice on the surface that is carbon monoxide that originally we would expect to see it as gas because it's one of these hyper volatile ones, the ones that even if the object is very cool or very cold, would be in the gas form instead of the ice form. So Chiron was like a puzzle. So why do we have some things that are icy and some things that are gas that do not really correspond with the temperatures that we would expect for the surface of this object?
If this is not what you expected, do you have any idea as to what could be causing this strange phenomenon?
Yeah, we have several different ideas, and that's the cool thing about Chiron, that it has so many different structures in the spectrum that it tells us very different stories. So for example, the methane, we think it is not on the surface, but it comes from layers under the surface, close to it, but below the surface. So that is why we don't see the ice on the surface. What we see is that the heating from the sun that is illuminating Chiron, it goes deep like a front that is penetrating the surface, and it reaches layers where the methane is contained in a molecule that is waterized and is liberated, and it goes free through the cracks to the surface. So that's why we see methane gas. For the CO2 is different, because for the CO2 we see both structures. We see bands of ice and we see bands of sublimation. And for the CO, what we see is only ice because we think there is a very small amount just located in a very specific part of the surface that still is cold enough to perceive the ice. So it's like different stories about different regions on Chiron, illuminated or not, heated or not.
Charles, do we have a sense of what the actual surface of this comet might look like? Can you describe that?
Yeah, so Noemi was alluding to like these ice absorption bands where in the spectrum there are features in different wavelength regions that indicate there is that ice present. As Noemi was saying, there's carbon monoxide, where carbon monoxide, due to this absorption band, we know it's somewhere on the surface. We don't have the resolved image of the nucleus surface. That's what we can't do because it's too far away. But the presence of this absorption means it's somewhere on the surface. Based on the closeness to Chiron to the sun, gives us the temperature on the surface. So we know that really in a lot of the surface is way too hot for carbon monoxide to survive. It should sublimate and turn into a gas, but it's surviving. So we know from that it needs to be closer to like a polar region. So one of the polar caps or somehow in a shadowed region. So by those spectral features, we can then infer things about the surface kind of indirectly. Well, we don't know for sure. That's like the puzzle she was alluding to. And so with other situations with the methane gas, like similarly with that, it's like it's not on the surface. It's coming from a deeper layer in the interior. So with Webb, we're able to like kind of put those pieces of the puzzle together to form a picture of what Chiron does look like or what the surface does look like.
Noemi, JWST is kind of the premier telescope. You're using it to see what is the makeup of this object, but there are still a lot of questions. Is this something that you will be able to get an answer to, or do you have to take an even closer look at this particular centaur to answer those questions and to put together the puzzle that you've laid out for us?
Well, yeah, there is a lot to do with Webb. It's like in the last 2 years, we have been leading different projects, and there are many planetary science trying to use Webb, and some of them are actually using it for the specific. But I mean, on these 2 years, we are scratching the surface and start to answer some of the questions that we had before with the knowledge. What happens is that every answer that we get and like every observation, it may answer one question, but it opens 2 or 3 more, like with Chiron. It's like, now we know what is on the surface, but we want to understand, is also, for example, ice on a coma around the surface of Chiron that may also be sublimating and contributing to some of these bands that we are seeing? How is it distributed? Is it all homogeneous around, or is it each gas is on a different region, you know? So for that, we have another project that is going on that is doing more observations, more detailed observations on Chiron. And I mean, I'm not going to, to spoil the result, but we are going to be able to go like one step ahead and answer some of these questions. So really, where each of these materials is on the surface, are they all mixed together or are they on different regions? Like Charles was saying, maybe a polar cap, maybe craters that have ice on the shaded parts. So a lot of mysteries that the Webb can still answer.
It seems like JWST is giving us more questions than answers, and that's okay for researchers like you, right? That is to be celebrated.
Yeah, of course. I mean, we are really enjoying that.
Charles, I'm going to ask you this question. I mean, absolutely no offense by it at all, but why does this matter? What does understanding the composition of Chiron mean in the grand scheme of understanding who we are and our solar system?
Yeah, so it's just a small piece in like a very big picture of understanding how our solar system formed. And so this is one of the larger, smaller bodies, kind of paradoxically to say, that it didn't form into one of the planets. So it preserves more of the leftover materials that were present at the beginning that are less altered than what they are in the planets. So this material represents more of a true picture of what this gas and dust that formed our sun and formed our solar system came from. And even going a little bit further, more recently, we've had the excitement of interstellar objects actually coming into our solar system. So comets and asteroids that didn't form in our solar system, but formed in other solar systems coming through. We're able to take observations as they orbit around our sun for a period of time or just go by close approach. And we're also able to like really characterize in high detail other systems forming in our galaxy. And so we're at this cutting edge of just knowing more about solar system formation, and Chiron helps us understand where's our placement in that? Like what other solar systems that we see forming have similar characteristics to ours? that could potentially provide the ultimate question of that solar system that we're observing has X, Y, and Z ingredients in it that look like our ingredients. So there could in the future be life in that system. And it's just, kind of interesting that we're now finally seeing how systems form and being able to link those to other systems that are forming elsewhere in our galaxy.
That's fascinating and super interesting. Noemi, I'm going to give you the final word here. Is a discovery like this and these follow-up observations that you've alluded to, is that possible without a tool like JWST, or is this really groundbreaking because of the technology that we now have that we can see farther and pinpoint these things in our universe?
Well, these particular observations were not able for decades on an object like Chiron, that was like actually the second transneptunian object discovered, because we have known it from the 70s. And it was puzzling even before, because we saw that it was active when it was farther from the sun instead of when it was closer. So that means that it is more active when it is colder. And we were trying to really uncover which were the materials that were triggering that activity and everything. And we couldn't do that. I mean, we scientists, we do what we can with the instruments that the technology gives us. And but now with Webb, it was like so easy. I mean, it's less than 1 hour of observations. And we have this beautiful, striking, and amazing spectrum with so many features that is going to give us the occasion of thinking and discussing for more than just this paper. This and many more have really been enabled by Webb.
Well, I am looking forward to hearing more about your findings with this fascinating object, a centaur, and getting us closer and closer to answering that ultimate question, are we alone? Noemi, Charles, thank you so much for joining us.
Thank you so much, Randy.
That was the research team leader for Chiron, Noemi Pineda Alonso, a distinguished professor at the Institute for Space Sciences and Technologies in Asturias, Spain, and Charles Chambeau, a research assistant professor at the University of Central Florida. That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do it on Apple Podcasts, Spotify, the NPR app, YouTube, or wherever you get your podcasts. Stay connected with this show. Be sure to follow us on social media. You can find us on Instagram and Facebook. We're at AWTY Space. And if you've got an idea for a future episode of the show, or you want to join us as a guest, reach out or email us, arewethereyet@cfpublic.org. You can find more space coverage online. Visit cfpublic.org/space. Are We There Yet is a production of Central Florida Public Media. Our producer is Marian Summerall. Our intern is Allison Castillo. Editorial guidance from LaToya Dennis. Support for Are We There Yet comes from our listeners. Make a contribution to this show and the other programs you get from Central Florida Public Media by visiting cfpublic.org. Until next week, I'm Brendan Byrne. Thanks for listening.